It is not easy to use mutexes efficiently. They partially serialize your calculation, so you might end up slowing down the calculation instead of speeding up if you use mutexes too frequently. So you have to think of a good parallel algorithm that minimizes synchronization across threads. Fortunately, in OpenMP, there is built-in support for one of the most common patterns in parallel programming, and that pattern is reduction. Parallel reduction is the application of an associative operator, for example, addition, to a variable. See how the variable total in this algorithm is shared across all threads, but the only way that these threads modify this variable is by adding an integer to it. OpenMP has a clause called reduction, which will allow you to specify the reduction operator and the variable. This clause is telling OpenMP that even though total is a shared variable, the only way that you're going to modify it is by incrementing it. So OpenMP will produce code that is highly parallel and at the same predictable. Think about what you would do if you did not have access to this reduction clause. If you just do not use the reduction clause, you will have a data race. Multiple threads are modifying the variable total at the same time, so you get unpredictable results. If you tried to protect this operation with a mutex, you would be serializing your calculation in every iteration. And you can try it. It actually slows down this particular calculation. With the reduction clause, performance is good and correctness is. The reduction clause works in a lot of practical cases. You can use it to reduce into a scalar, or as of OpenMP version 4.5, you can use this clause to reduce into an array. But sometimes the reduction clause is not sufficient because, for example, the type of the variable or the nature of the operator is not known to the OpenMP. So it is useful to know how reduction is implemented behind the scenes. Typically, it is implemented using thread private storage. If my goal is to increment the variable total by multiple threads, I will create a temporary variable in each thread in which I will run the running sum. At the end, I will end up with multiple partial results, and my goal will be to reduce or aggregate these partial sums into the total sum. And I will do it by adding the partial sums to the shared variable, and this time it is justified to use an atomic construct or a critical section to protect this data race. This diagram has variable names x0, x1, x2, and so on. Of course, this is not practical for programming with OpenMP to have different variable names. Instead, you will use thread private variables, like in this code listing. As you can see, the variable total is shared, but total THR declared inside the parallel region is thread private. For the partial sum, I use total THR, and after the loop ends, I reduce partial sums into the total container. Remember that every thread is going to run this line of code, and I protect it with an atomic construct because it is a data race. This data race, once again, is resolved with minimal synchronization because I'm only going to have as many synchronization events as I have threads. It is possible to further improve the reduction algorithm. You can, for example, do tree reduction, where instead of as many mutexes as you have threads, you will only have a log of threads for the number of mutexes. But as long as the bulk of the calculation takes much more time than the post-processing, then the linear algorithm will do just fine.